Holographic gravity. Gravity is traditionally understood as one of the fundamental forces of nature. In Einstein's general relativity, it is described as the curvature of spacetime caused by mass and energy. However, what if gravity is a holographic phenomenon? What if gravity and spacetime curvature emerge from informational processes occurring at the boundary of a massive object? To address these questions, we explore the concept of Scaling Entropy-Area Thermodynamics, SEAT, a published framework representing a significant paradigm shift in our understanding of gravity. SEAT, a peer-reviewed model developed by Olivier Denis, draws inspiration from Eric Verlinde's concept of emergent gravity, but Denis extends it into a comprehensive framework that generalizes the holographic principle to all gravitational systems. This generalized principle elucidates how quantum gravity and spacetime curvature emerge from informational processes at boundary surfaces. SEAT aligns well with Verlinde's theory of emergent gravity, which proposes that gravity arises as an entropic force. But while Verlinde emphasizes the bulk properties of spacetime and how matter influences entropy, SEAT focuses on the boundaries, highlighting the structured information at these surfaces to explain the emergence of quantum gravity. Central to SEAT is the idea that in gravitational systems, entropy, a measure of disorder or information, scales with surface area rather than volume. This concept builds upon the Bekenstein-Hawking entropy of black holes, which asserts that a black hole's entropy is proportional to the area of its event horizon. According to the holographic principle, all the information contained within a volume of space can be represented on the boundary surface that encloses that volume. This principle underpins the Bekenstein-Hawking entropy formula, which posits that the entropy of a black hole is proportional to the area of its event horizon, not its volume. SEAT extends this idea, suggesting that not only black holes, but all gravitational systems have their entropy fundamentally linked to the area of their boundary surfaces. Moreover, SEAT addresses the black hole information paradox by suggesting that black holes evolve towards increasing order as their entropy decreases, with information preserved in a progressively organized manner and emitted through entangled Hawking radiation, this radiation being in pure state and entangled with fields inside black hole preserving all initial information encoded in a structured and organized manner, allowing us to extract information from black hole's interior. This perspective implies that black holes, far from being chaotic, evolve into highly organized systems as they lose mass and energy, preserving information through structured processes. Those considerations being illustrated by rigorous mathematical derivations presented in the published article. The generalization of the holographic principle by SEAT is facilitated by concepts such as the Ryutakaya-Nagy formula and new formulations involving surface gravity from and within SEAT framework. SEAT proposes that gravitational entropy universally scales with surface area, offering a compelling explanation for the emergent nature of gravity and spacetime curvature. By linking entropy, information, and spacetime geometry, SEAT suggests that gravity is not a fundamental force, but rather an emergent property arising from quantum statistical mechanics. Mathematically, SEAT demonstrates the connection between gravitational properties and thermodynamic principles by deriving an entropy formula that depends on surface gravity, mass, and horizon area. This formulation shows that gravitational systems can be understood through thermodynamic principles and informational dynamics localized at boundary surfaces. In this framework, entropy is not only a function of the horizon area, but also depends on mass and surface gravity, underscoring a deep relationship between gravitational and thermodynamic properties within the context of quantum gravity. SEAT extends the holographic principle by proposing that the entropy, and therefore the information of any gravitational system, is fundamentally linked to its boundary surface. To bridge this concept with the broader understanding of gravitational behavior, SEAT also suggests that the orderly structure of information at the boundary plays a crucial role in shaping the dynamics of surrounding space. This orderly information structure on the boundary exerts an entropic influence on the surrounding space, causing nearby objects to follow paths that align with the entropy gradients. This carefully organized configuration encodes information about the object and its gravitational field, structuring the surrounding space's entropy in a way that naturally directs objects along paths that follow this entropic order. The entropic order refers to the level of organization in the informational structure around an object, ultimately altering the geometry of the surrounding space. The holographic emergence described by Seat unifies gravitational systems of all types, whether bounded by horizons or not, emphasizing that gravity and space-time curvature are emergent phenomena driven by the structured organization of quantum states at boundaries. Thus, massive objects curve space-time not through intrinsic gravitational forces, but through entropic effects resulting from informational processes at their boundaries. The Seat framework unifies quantum information theory, thermodynamics, and gravitational physics, presenting a revolutionary perspective where gravity emerges as an entropic effect driven by the structured organization of quantum states at boundaries. The holographic gravity paves the way to a completely new understanding of gravitational systems, explaining quantum gravity and space-time curvature as emergent informational processes at the boundary surface. Here is elucidated gravity as holographic gravity.